So far we have discussed the necessary condition for design using pole placement technique. And what is the necessary condition? Necessary condition states that we require the system to be completely state controllable. The system which we have considered here in this is x of k plus 1 is g into x of k plus h u of k. Right. So this is the system which we require to be completely state controllable to determine the matrix K, so that the pole locations can be placed, or that the poles can be placed at various desired locations. Now that is the necessary condition, and if it is not controllable, then it is not possible. There are a few eigenvalues which the feedback matrix cannot control the eigenvalues. Few eigenvalues. Right. The sufficient condition states that the system, if the linear time invariant system considered is completely state controllable, if this is controllable state, then it is possible for us to determine a feedback gain matrix K, to place the poles. So now that is the sufficient condition, right? So completely state controllable, necessary condition is it should be completely state controllable, and sufficient condition it is if the system is completely state controllable, then K we are able to find out K, right? So now let us see what is this complete state controllability, or in this sufficient condition what is possible for us here. Now we have this equation Zi minus G, which is the original system, which is the characteristic equation of the original system, which if it is equated to 0, then we are going to get z power n plus a1 z power n minus 1, a2 z power n minus 2 plus so on, a n minus 1 z plus an. Now choose a matrix or the transformation matrix. In the previous case we have discussed that P is the transformation matrix where a few state variables are not controllable, but here we have all the state variables to be controllable. Therefore I am choosing a different transformation matrix T, which is nothing but M into W, where M is the controllability matrix. M is the controllability matrix, which is H, GH, G square H, G power n minus 1 H. This is the controllability matrix H, and whose rank is n. Because it is completely state controllable, rank of M, rank of T is, or rank of M is equal to n. Rank of M is equal to n, and W is given as a n minus 1, a n minus 2, a 1, 1. Similarly, a n minus 2, a n minus 3, 1, 0. Therefore, a1, 1, 0, 0, 1, 0, 0, 0. Okay. Now this is our W. Let us choose this as our matrix. Now because we have this transformation, we can find out when the transformation is existing, we can find out the matrix T inverse GT is equal to G cap, and from the controllable canonical form, the matrix obtained for us is 0, 1, 0, 0, 0, 0, 0, 0, 1. Okay. Then minus an minus 1 minus a1. Now this is the G cap for controllability matrix, and T inverse H is from the controllable canonical form. we have this as the controllable canonical form, which we have discussed in our previous classes. The controllable canonical form, you can have this 0, 1. T inverse H is 0, 0, 0 and 1. T inverse ut, and this is nothing but H cap. This is H cap. Right. Now from this matrices, now we have this equation as our characteristic equation, as our initial characteristic equation of the original system's characteristic equation, which has got no feedback. And now when we are applying feedback to this, what is the equation that we are going to get here? When applying feedback, we have Zi minus G plus Hk minus G plus Hk. Now when we are applying again, T is equal to mW. When we are applying transformation, what is the matrix that we are going to get? Zi minus G cap plus H cap K cap. Right. So, and K cap is equal to KT. K cap is equal to KT, and this can be given as the equations del n minus 1 and del 1. Now these are the things, let us choose, these are unknown variables to us. Now we require to find out K. T is known for us, T is m into W, we know those values. K is the only matrix which we doesn't know, and let us choose del n minus 1 to del 1 as our matrix K into T. From that we can obtain K. Okay, now M is known, W is known, or G cap is known, H cap is known. We know G cap, we know H cap, we know K cap, I is also known. Then we can find out what is the matrix now for this transformation. When we have transformed these equations, and we will be getting Zi minus G cap plus H cap K cap. The determinant, if we obtain, we have this as Z into 1, 0, 0, 0, 1, 0, 0, 0, 1 minus G cap is that 0, 1, 0, 0, 0, 0. Right. I can also write one more because we require that to be much longer. 0, 0, 1 and minus an minus 1 minus a1. Okay, plus H cap. H cap is 0, 0, 0, 1 and K cap. K cap is del n minus 1 del 2 del 1. Now the determinant of which is obtained, it should be found. Now you can add this Z 0, 0, then 0 minus 1 and 0, then remaining are zeros, therefore you can write zeros, 0 and so on zeros. Then 0 Z, this is 0 because 0 minus 0 plus 0, and here Z into 1, 0 and 0, so this is Z here, and remaining are zeros. You can say we have probably 1 here, therefore I can put here as minus 1 because 0, 1, 0, 0, 1, 0, 0, so on 1, therefore that minus 1 can be put here and the remaining can be gone to zeros, right? And after which again 0. You have no zeros here, all zeros only at this point, right? And we have this as the last second part, last second row. Last second row we have this as 1, right? Last second row we have this as 1. Okay, so 0 or zeros, z into minus 1, again you have this 0, 0, 0 and 0. You have somewhere again z and minus 1, right? And 0, you have here z, the first row is 0 and 0 minus of minus an plus del n. Here you are having an plus del n, right? Because z into 0 minus of minus an plus 1 into del n. So an plus del n. Similarly, an minus 1 plus del n minus 1 and an minus 2 plus del n minus 1, so on. Okay. Then we have here again z plus a1 plus del 1, z plus a1 plus del 1. Now this is our equation and we are going to get this. When you equate this to 0 or the determinant, when you find the determinant of this equation, when we find the determinant of this equation, what do we get? Z power n plus a1 plus del 1, z power n minus 1 plus a2 plus del 2, z power n minus 2 plus so on plus an minus 1 plus del n minus 1 z plus an plus del n equal to 0. Now this is the equation which we have obtained from this equation. Now let us consider mu1, mu2, so on. Mu n are the eigenvalues of the matrix of the system of the characteristic equation. Eigenvalues of our linear time invariant system, which we have to place it in the desired location. Our desired location is nothing but g minus g cap plus g minus g plus hk. Okay, this is where we want to place our location. So we can write this as z minus mu1, z minus mu2, z minus mu n equal to 0. This can be written as z power n plus alpha 1 z power n minus 1, alpha 2 z power n minus 2 plus so on plus alpha n minus 1 z plus alpha n equal to 0. Okay. Now when we equate these two equations, equating these two equations and equating the order of these equations, we have alpha 1 is a1 plus del 1, alpha 2 is a2 plus del 2, so on, alpha n is an plus del n. Right. Now we require only del. These values are required. So del 1 is alpha 1 minus a1, del 2 is alpha 2 minus a2, del n is alpha n minus a. Now alpha 1, a1 are known, alphas, all alphas and a's are known, and we can find dels from these matrices, from these equations. So when you are equating these two, because these are the closed loop desired poles, these are closed loop desired poles when you are applying feedback k, right? So you can find out easily from this values. Therefore, if the system is completely state controllable, it is possible for us to find K matrix, K cap is equal to KT, which is nothing but del n minus 1, del 1, right? And T is also known for us. T is MW, M is the controllability matrix, and W is the matrix which is obtained from the original matrix, right? And therefore del n del n minus 1 are to be found, and for that we can find out del 1 del 2 del n from based on these equations obtained from this. Therefore this is the sufficient condition. So for the system, to design a system for pole placements or pole assignment, it is necessary and sufficient for the system to be completely state controllable to determine the state feedback gain matrix K, right? Once we have found the gain matrix K, then it is easy for us to find out the pole place, to place the poles in the desired locations. Now this is one technique where we are going to use for one technique for pole placement or pole assignment, and eventually there is another formula, another method also, which is called the Ackermann's formula, which we will be discussing in the next class.